Good evening, everyone. Hi. Perfect. Hello. Welcome. Hello. Welcome to the University of Manchester, and thank you so much for joining us.
Are you expecting a microphone to be working? Because it isn't.
It isn't working. I'm very sorry. Can you hear me at the back? Perfect.
Speak up.
I'm sorry. My colleagues will tell me I'm not very quiet, but I think I am normally. My name is Olympia, and I am a development officer within the Division of Development and Alumni Relations. It's quite a lovely evening to be here to welcome you all. Today officially marks 1 year since I started with the Alumni Office, and it's a lovely way to celebrate by welcoming so many of our alumni community and friends back to the University of Manchester. So thank you for joining us. Before we get going, I have a couple of housekeeping rules that I just need to run through with you. So first of all, please can you ensure that your phones are on silent? Thank you. And secondly, just to let you know that there are no planned fire alarms this evening. So if there is a fire alarm, please can I advise you to leave the building calmly and head out via the main entrance out onto the grass outside, which is Humanities Bridgeford Street. Now I have the great pleasure in introducing you to our two speakers. Our first speaker is Professor Tony Payton. Tony has 30 years experience on a diverse range of electromagnetic sensor systems, and he has been the principal investigator in national, international and industry-funded projects. He's also been a partner on many EU projects as well, and has co-authored almost 140 international papers on electromagnetics and sensing. Tony will be followed by Dr. Liam Marsh, who graduated from the University of Manchester, and his research interests include many aspects of metal detection and has included the design and construction of a system that detects iron-rich meteorites in the Antarctic, as well as an ongoing study developing a prototype system capable of measuring ice thickness in rural communities. Now, at the current rate, it would take more than 1,000 years to rid the world of landmines. So the pioneering research being undertaken by our speakers has the potential to save millions of lives. So it really is a pleasure to welcome you both to speak. Thank you so much for taking the time, and I'd like to welcome Tony.
Thank you. I'm not quite sure I can follow that, but well, first of all, just a little bit about this talk. As you've heard, my name's Tony Payton, and it's a pleasure to be able to talk about part of our research. And also, thank you for coming along. It's been a lovely day, so it's extra special to make the effort. So this work really is, although there's myself and Liam, it's really the results of many people that are involved in our group, and some of them are at the front. So we're just the ones getting to speak about it, but really lots of other people have done the work. We're also very grateful to our sponsors, a charity that Sir Bobby Charlton founded, and also the Mines Advisory Group, who are based here in Manchester, who won the Nobel Peace Prize. I think it was no, I better not say the year because my memory might be mistaken. So just a little bit of an outline of what we've got planned. I hope it'll be fairly varied, and I hope you'll find it very interesting. We're not going to go too deep into the technology, but we'll hopefully give you enough so you understand whereabouts we are and what the challenges are. So I'll say a little bit about our involvement in this research, then hand over to Liam, who'll talk about basic facts, metal detection, and then we'll swap again, and I'll talk about ground penetrating radar, integration, precision measurement, and how and what type of systems we can look forward to. So where a little bit of where we started. This really is going back it's probably about 8-9 years ago. We were involved in a lot of research on security scanners. So I thought I'd start with metal detection, and something you'd probably be able to relate to. I guess you've all walked through these type of portals at airports and various places and stood in security queues and so on. Basic metal detectors. Well, one of the problems with metal detectors is that's just what they do. They detect metal, so you know, every alarm has to be investigated. Also, the security staff don't know exactly where to look, so that's also a little bit of a problem. We started this by applying sort of the theory of metal detection a bit more deeply, and I'll sort of show you the results really, because the videos hopefully explain it for themselves. So what we're going to look at is this nasty little item here. It's an opinel knife, and what you'll see is Liam. This was 8-9 years ago. Not aged much. He's just picked up a knife, walked through the metal detector. It didn't beep. He's going to walk through the metal detector again, and you'll notice just on the right there, it's turned red to show it's alarmed. And then you'll notice the computer go away and do some calculations. If you watch the screen, there you go, some numbers, and it's produced this video here. So what we've actually done there is we've taken all the data from the metal detector, and we've calculated it, and what we've done is we've worked out the trajectory, the path that the metal object has taken through the detector, and we've also worked out what the signature of the metal is. If we know the signature of the metal, we can then start to classify it into different types, and that's sort of indeed what we do. So what this, I'll just sort of show you the output. What it's producing is a video sequence, and the spot is the 3D coordinate sequence projected into the frame of reference of the camera, so you can see exactly where the knife is. There's two spots, one on the front and one on the back. The one on the back is actually pointing through Liam to the front pocket. We were a little bit lazy. We know it's not on the back. We could turn that off, but we just wanted to show the principle, so we left it on. And in addition to that, what we get is this the characteristics, the signature. I won't go into too much of the theory of what that object is, and then we can compare that against libraries of different types of objects and say, yeah, that's characteristic of a knife, it's characteristic of a phone, it's characteristic of loose change or keys, and it was surprisingly good how well you could classify items that way. So that's sort of what we were doing about 8-9 years ago. And obviously it's an area we're still active in research. What I'd like to do now is just show you a video, because shortly after that we got approached by Sir Bobby Charlton and Mines Advisory Group about, well, you know, you're doing this sort of work, could you apply that to humanitarian demining? Because metal detection, as you'll hear, is part of the problem. It's not the entire problem at all. It's not the entire solution, but it's a small part, and it's a potentially an important part of the solution. So I'll show you this short video, and then I'll hand over to Liam.
So I'm just going to take over this bit of the talk now, and I'm going to start just by talking through some of the basic facts about landmines, and then I'm going to move on to talk about some of the metal detection technology. Now, we have some instrumentation set up at the front here, and risky as it may be, we're going to attempt a bit of a live demonstration later on, so I hope you'll bear with us at that point. But to start off with, just to give an idea as to the scale of the problem, it is estimated that there are over 110 million landmines buried and unexploded in the world. Now, the truth of the matter is, nobody knows how many landmines there are in the world. It is impossible to give an accurate description. We don't know if that number is particularly relevant. We know that it's of that order of magnitude. Okay, there's some disagreement amongst experts, but what we do know is it is tens of millions, possibly of the order of low hundreds. The problem is it's a lot. Whichever way you look at it, it's a very, very big number, and they are spread throughout the world. Some 68 countries report landmines. That does not include unexploded bombs. Okay, so that doesn't include UXO, unexploded ordnance. And also that doesn't include improvised explosive devices, which are becoming more of a problem. A key distinction worth making, a landmine is a manufactured product. Okay, think of it as something that people are able to make hundreds, thousands, tens of thousands of copies of, whereas an IED is by definition improvised. It is something which is more or less a one-off product. Okay, so we're talking a big distinction there between those two. One is the known, one is very much the unknown. And it's a sad fact that Africa is by a very long way the most heavily mined of all the continents. And it's estimated that 37 million mines, approximately 1/3 of the world's landmines, are present on the continent of Africa. If we look into that a bit further, we say that we have mines in 68 countries. It's reported that between Afghanistan, Angola and Cambodia, between 3 nations, we have 85% of the world's casualties from mines. Okay, now there are a lot of reasons for that, far more reasons than we can possibly go into tonight, but principally it can come down to education, it can come down to mine awareness, how well educated is a community about the threat of landmines, how well can we identify where there might be landmines and secure that area away so that people can't go there. But there are other more subtle factors. You know, what are people doing with that land? Are they reliant on that land for farming? Are they reliant on it as a means of transport? And unfortunately, there's a correlation there. And as a further point here, Angola alone is estimated to have 10 million landmines. So in one nation, we have a very significant proportion of the world's landmines. Point 4 here, again, is something it's very, very hard to put an exact number on. Landmines vary. You have different landmines. There are hundreds of different types of landmines, and they are all in different areas of the world. Some might be submerged in water, some might be exposed to rain, some to sun, some to shifting sands. The reality is how long a mine survives will depend on what the mine is, where it is. And although we say a mine may be active for decades, some mines like bombs will be inert, they'll be duds. Others we see across North Africa. El Alamein is a particularly good example. We still have dangerous explosives from when the days of Rommel and Montgomery were fighting one another there. Okay, so they do present an ongoing danger. Point 5, just to touch on the economics. We talk about a manufactured product. A landmine costs of the order of $3 at its cheapest to produce. But to the international community, the cost is between $300 and $1,000 to clear. Okay, and that financial cost does not reflect the fact that we have to put people in harm's way to do that job. So it has a financial cost and also a human cost. In terms of where mines are in the world, we can see here they're spread all over the world. We see, as I said on the previous slide, we have a huge amount of mine contamination in Africa, but we also see it in other areas. We see it in South America, we see it in Far East Asia, and perhaps in some areas which might be a bit less familiar to us, some areas where perhaps we holiday, perhaps we may have visited. If we look in the inset up here, we have Croatia, and in the inset down here, we have Turkey, both showing what is being described as massive mine contamination. And of course, we see Angola as well down at the bottom here, showing massive mine contamination as well. The point of this slide is to show that these problems don't belong to one particular country or one particular part of the world. It is a universal problem. And anywhere shown in grey is a nation that hasn't reported data. That doesn't mean there's no landmines there. Okay, some of them we know there are landmines there, but we don't have an estimate on how many there are and what the contamination is. In terms of the types of landmines, I touched upon this earlier on. There are literally hundreds of different types of landmines. We split them into 2 different categories in terms of what their application is. We have anti-personnel mines. They are designed to be triggered by people. And we have anti-tank or anti-vehicle mines. They require a heavier mass to trigger them. So they are not triggered by people, but they will be triggered if a tank or if another vehicle drives over them. The important thing about anti-personnel mines is they don't discriminate which person treads on them. Any person can set off an anti-personnel mine. Any animal of a certain mass can set off an anti-personnel mine, and they do, all over the world. I've got some examples down here of anti-personnel mines. When we talk about them, this is the size, this is the order of magnitude of an anti-personnel landmine. If I just briefly flip over to the visualizer down here, if I show you an anti-personnel landmine in my hand, it's very small. but it is deadly. Okay. You'll find often we have different colours. They're camouflaged, typically camouflaged. And so they are very, very small, and they are very, very hard to find. In terms of where or who has been using landmines, I've got this slide in here from the International Campaign to Ban Landmines. This isn't necessarily here for the purpose of politicking. It's here to explain that nations all across the world have historically used landmines. Anybody in red is known to have used landmines in conflict or in other circumstances. We see here there's a differentiation between government level and non-government groups within the state. Again, the point of this slide is to show that landmines have been used by nations all across the globe. And so if we start to talk now about why it's so hard to find landmines, the main issue is that it's an overwhelming problem. Okay, we've already said there are estimated to be 110 million landmines in the world. We don't know where they are. We know roughly where a lot of them are, but actually to find them, we don't know where they are. So we have a lot of targets to find, we don't know where they are, and actually a modern landmine, and when I say modern I mean recent decades, not recent years, is almost entirely plastic. It has a very, very small amount of metal inside it. And that's been done deliberately because metal detectors are on the front line of mine detection. If we talk about the amount of metal that's in a mine, we have a surrogate here that I can show you, where we have a blue liquid in which we are representing the explosive, and then we have a black dot in the middle just here. That is our metal content that we're looking for with a metal detector. Okay, the overwhelming majority of this mine surrogate, is not metallic. Now this surrogate's particularly useful because actually two of the technologies that we are demonstrating here tonight, metal characterization and ground penetrating radar, for both of those, this is a particularly good representation of what a target might look like. We've got some metal, we've got this jelly that mimics the explosive, and then when we put the lid on here, we have a slight air gap, and that air gap represents the area in which the force will be pressed to detonate the mine in the first case. So we have all of the different components of a landmine, but with none of the explosive. So I should stress as well, sorry, while I'm talking about this, when I showed you these earlier on, for the avoidance of doubt, these are mine surrogates. These are not live landmines. It would be a different kind of risk assessment altogether. What I can do, I can ask my colleagues on the front row to perhaps pass that back if anyone wants to have a closer look at exactly how much metal we're looking for in a mine. Please, by all means, have a closer look. And so when we talk about that, we can see a real landmine, and we can see exactly how much metal there is in a real landmine. We've colour-coded this. We only need to have the red bit. That's the only bit that is common to all landmines. And we do have other parts. We have the parts in blue, which may be there, and the part in green that for this particular landmine is actually removed to arm the mine. So again, reinforcing the point that the mine is overwhelmingly non-metallic. So you might ask, well, why do we want to clear these landmines then? It's very hard, there's a lot of them. If we know roughly where they are, can we not enclose the land and just leave them there and sort them out later down the line? And the problem is that actually, even where that happens, people still fall victim to landmines. And the sad truth is that children disproportionately fall victim to landmines because they are naturally curious. Okay, that curiosity that we encourage can sometimes mean life or death in the wrong circumstances. You've seen what these surrogates look like. To a child who doesn't know about landmines, that might look interesting, that might look like something that you can pick up. Unfortunately, it does happen, and that's when accidents happen. So it is important that we find these landmines. It's not a problem we can just park up and sort out in years to come. Where children are concerned, landmines are far more damaging than they are for adults. Okay, landmines are not designed to kill adults, they are designed to maim adults. Most of these minimum metal anti-personnel mine surrogates and the mines they represent would cause serious damage to me below the waist. It's very difficult to say specifically where, because it depends how deep the mine is, it depends exactly how I've trodden on it, what protective gear I've got on, but the fact is I would very likely survive treading on a landmine, and that is deliberate. It makes them cheaper to make, it's less explosive, and it also presents a burden to the state that is caring for me. But for children, damage in this area, up to 1 metre, is fatal more often than not. In terms of not the damage that they cause, but in terms of the other problems that we have associated with landmines, it is widely acknowledged that they deny access to vital areas of land that people could use, particularly in developing communities, that could be used for growing food or for building houses, or even perhaps on transit routes. What's perhaps less widely known is that it discourages outside investment when you have the presence of landmines in a mined area. Okay, companies who are looking to place offices in areas or looking to move staff through areas are put off doing so where they will face the risk of landmines, and that deprives vital investment. And so comes the fairly logical question that we get asked an awful lot: can we not just get a massive machine, send it into a minefield and just smash the ground to pieces? Yes, but also no. Like everything with demining, it's yes with a bit of no. Manual clearance is a possibility, but there are other problems that are associated with it. If we look at some of the things that go out and find landmines, this here on the right is a mine flail. That will sort of spin those chains around, they will whip into the ground, and they will essentially churn up the ground and obliterate anything that's in there. Okay, it's an effective way of clearing land. There are a few problems. Getting something of that size into a minefield is extremely challenging. Do you have the roads to get it there? Do you have the bridges to cross? First of all, can you afford it in the first place? And finally, all of this at the front end of the flail is essentially consumable. Once that's beaten away at the ground and seen a few landmines, all of that needs to be replaced and maintained. So it's an ongoing significant cost. What is perhaps a little bit more subtle is more visible in this image on the left. We see both of these are on nicely cleared ground, but actually this at the back is more what you would expect of a minefield. Okay, a minefield is somewhere people have not been for a long time. They look more often like that. Okay, you're looking for that in that. It is extremely hard. And so we can't just send machines directly in. And even when we do send machines directly in, we're talking about humanitarian demining. Okay, we need to make sure there are no mines there. We can't just send a machine in. Someone has to follow that machine and walk that ground and check there are no mines there and investigate all of the metallic clutter that's there. Now imagine you've just sent a machine over to obliterate all of the object in the ground. You've potentially given yourself many more bits of metal to find than you would have had otherwise. Okay, so it's a yes and it's a no. It can help, but there are consequences. In terms of these machines in action, we have a couple of videos. This here is showing anti-personnel mines being cleared. So you can see it doesn't trouble the machine terribly. It's on already prepared ground. If we compare that with an anti-vehicle mine, this is a TMA4, this is a much larger mine. Okay. When we talk about the consumable nature of these machines, they have to withstand these sorts of blasts and the other sorts of blasts. Okay, we are asking a machine to do a heavy-duty job as well. So it's not something that can just be solved by machines. In terms of metal detectors, I've already said they are on the front line of landmine detection. They are used all over the world. But as I've already said, landmines contain such a little amount of metal that we are very, very challenged in terms of what we're going to find out there. We can, with the latest standard of commercial metal detectors, just about detect the metal content in a minimum metal landmine. The problem is, when you make a metal detector that's good enough to do that, you make a metal detector that can find any bit of metal, any innocuous bit of metal. And the fact is, particularly where you're looking at a former conflict zone, the area will be littered with scrap metal. You might have bullet casings, you might have fragments of exploded bombs, you might have even things like mess tins, all sorts of other targets that all need to be investigated. And so what you have is a very sensitive metal detector that is set off by all sorts of metal particles. Now, it's all well and good to say that, but if you're that person in that minefield and your detector is beeping, you need to assume that each of those beeps is mortally dangerous. But actually, if we dig and look back at the mining that was going, or the demining that was going on in Cambodia in the mid-90s, it was reported to the UN that for every one viable landmine that was excavated were 129 bits of metal that were not a landmine. Okay? This is in Cambodia. Okay, this is people in protective gear, potentially in a very hot climate, digging up 129 things that are not a landmine to find the landmine. It's one way of solving the problem, but it is not a way we should accept. Okay. So I'm going to just move on now to talk a little bit about metal detection and to introduce the demonstration that we're going to show down at the front here. I've got a very brief animation that just shows a metal detector going over the ground with a landmine model in there. And what we see on the left as it goes across is we see some points. As we go over the landmine, our metal detector jumps up. It starts down at 0, it jumps up when we go over the mine, and we come back down again. Now, a basic metal detector would say, okay, if we're above somewhere here, we'll beep. We'll tell you there's some metal there, and then it's up to you. Okay, that's the sort of output that you get from a basic metal detector. Looking at that in a slightly different way, if we look at it on this sort of graph here, from a normal metal detector, you can extract two parameters. We see one here and one here. And what happens is when there's no metal, that's close to 0. And when there is metal, it sort of bobs up and down. Okay, and the one at the bottom, we have the amplitude of a signal, we have the phase of a signal, because both of those are affected by the presence of a mine. So all we're seeing there is a point that's going up or down on whether or not there's metal there. So it's metal detection. So it's up to the human to find out what has caused that to happen. The reason that happens is because the simplest of metal detectors, if we use the example of the one here, they're sending out a signal into the area around the detector. Okay, they're being excited at a particular fixed frequency. The example I've given here is 5 kilohertz. That's not atypical, but it'd be of that order of magnitude. This is going into the area around the detector. It's interacting with the metal object, and we detect what the interaction is. Okay, so we know all about what's happening at 5 kilohertz. What we don't know is what's happening in all the other frequencies that exist in the world. And so what we do is we implement something called spectroscopy on this detector, which is where we put more than one frequency in. And actually, our signal that we send out looks a bit like this over here. It might just look like a load of noise, but you have to take my word for it. This is what happens when you add lots of different signals together. And what that means is that when we're sending this out into the area around, we can actually get more information about what metal we're detecting. Instead of that one lonely point on the spectrum here, we've actually got a continuous trend. And where we have a continuous trend, we can start to identify features. And so, hopefully, it's clear from that why this is useful. By having this information, we can identify features of objects. We can tell the difference between a landmine and metallic clutter whilst it's still in the ground. Okay, it offers the potential for us to do this. But, and there's always a but, we can't just keep shoving more frequencies in there. The more frequencies we put in, the more we divide the amount of energy we have down. We have two options. We either flatten a battery very quickly, that's not really possible, or we divide down the amount of energy we have. So there has to be a trade-off. We have to trade off one factor against another, which signal is important to us, which can tell us the difference between a landmine and the objects that are not landmines. And I've provided some examples here. I don't really go into too much detail here. The point is we have at the top some landmines, then we've got some clutter, some bigger clutter, and then some very big clutter. Okay, a mortar tail is not dangerous. It's part of a used mortar bomb. It's a large piece of metal. The point here is that although these might look similar, they are all distinct. They all have lumps and bumps in different places. And actually, if we take the parameter on the left, we see we have a mine here and the same mine here. It's two different parameters we extract, and we plot them in a slightly different way. This is where we can really start to pick into how the objects look different. If we look at the ball bearing, all of these different frequencies that we're pointing out here, each of these represents a signal from a different component. They're all pointing down to the bottom right. All the others are pointing to the bottom left. Straight away we can see that's distinct. The others are a little bit more subtle. If we look down here at the landmine, we see these other four are bunched and they're further spread up here. But also, if we look here at the order of them, we have red, then green. At the top here, we don't have the same colour ordering. Okay, they are distinct. These are all objects which we can measure and we can tell, without knowing what the object is, which object is which. Unfortunately, that's only part of the problem when it comes to metal detection. I'd love to say that was everything, but actually we have a far greater problem, and that's what's called uncooperative soil. And that makes it seem, like it's a bit of a nuisance, but actually it's a really, really big problem. Okay, we've seen how much metal there is in a landmine. Uncooperative soil is what we'd describe as mineralized. It has deposits in it, perhaps iron. We're talking about things which will perhaps trigger a metal detector. If you've designed a very, very sensitive metal detector and you put it over a ground that's filled with iron particles, it is going to squawk absolutely everywhere. To put this into context, this is what our landmine looks like. This is a landmine buried 5 centimetres into the ground. If we look at the numbers here, we're sort of between minus 0.02, 0.04. If we look at the ground, I've taken the colour out of this figure because it's meaningless at this point. We're now at 3 and 4. Okay, the magnitude, if we inset that at the top just for as a reminder, the ground itself is 100 times more responsive than the landmine that we are looking for. So it's not just enough to make a metal detector that can find the landmines. We have to make one that's intelligent enough to tell the difference between this over here and this up here. And they do superimpose. So when we go over a landmine, those blue phases will all deflect according to the landmine, and they will deflect by that much. Okay? We've helpfully inset in the corner here. That orange vector there is how much each one of those lines will move in the presence of a landmine. Okay, they are very, very hard to find. And it's these tiny changes that the algorithms that Tony will be talking about later on are looking for. So I hope that puts that into some context. And now, with some trepidation, now we're going to seamlessly flick over. I'd like to acknowledge my colleague Wouter van Verre down here, who is driving the metal detector. As an example, I have a piece of ferrite here. This is a piece of magnetic iron. I can put this into the metal detector. We see it drags all of the phases over here. That's a little bit like the ground. Okay, take that away. I have a landmine surrogate, let us remind. If I put this inside, we see we're somewhere quite different. If we take any other metal object, I have a pointer here. Again, we have a box of mints down at the front here. You can see we can tell the difference between these objects. In fact, we can even tell the difference between different landmines. This is a Type I A72 landmine. You see we're in this direction. If we take the M409 landmine, we're over here. Okay. So I hope that's a useful demonstration of the principle of spectroscopy. And at this point, I'm going to hand over to my colleague, Tony Payton, who's going to continue from here. Thanks, Lou. Thank you.
in a minute. Okay, so you've heard about metal detection moving to metal characterization. The problem is just relying on detecting or characterizing the metal alone still is not enough. So if you can combine it with another sensing modality and get two positives at the same time, one from metal and one from, say, the plastic casing, then you can be a little bit more sure of what type of device you're actually looking for. So the latest generation of mine detectors are what's known as dual mode, that are sort of starting to find their way into the field. And they're a combination of metal detection plus ground penetrating radar. And as you've just seen, we can do a bit more now with metal detection and move it towards metal characterization. So what I want to do for the next 10-15 minutes is talk about ground penetrating radar, and then I'll talk about how we can take those two a little bit further. Ground penetrating radar is a particular type of radar system. It's very distinct from the normal sort of radar that you'd associate, for example, with air traffic control or military detection of jet fighters and missiles and so on. And the basic approach is there's a transmitter that sends a signal out, and there's a receiver which receives it. And what you're actually looking for is you're looking for a reflection of a target that's buried in the ground. Now there can be many things that can affect this, and I'll show you the four main components. First of all, you can have some residual signal that finds its way from the transmitter to the receiver, some direct signal. Then you can have some signal which is bounced off the ground, which we'll call ground bounce. Then there's signal you want, which is bounced off the target. But the problem is there's lots of other things in the ground. There's rocks, burrows, tree roots, and so on. The ground's not maybe not be homogeneous. So there's what we call clutter, which comes from a whole variety of different sources. And all these four sources superimpose. So what that looks at in terms of the signal, and what I'm showing you here is an A scan. So what we've got on the x-axis is time in nanoseconds. And because these signals are travelling at a certain speed, time in nanoseconds really translates to distance. And you'll see shortly what that actually means, what that translates to. So what we're seeing here is the blue trace is when there's no target. If there's a target based very close to the ground, you'll get a signal back that's a red signal. You can see they're slightly different. And the problem is the mine's on the surface of the ground, so the mine is sort of superimposed in part of the signal, which is the direct coupling between the transmitter and receiver, and part of the signal, which is a ground bounce. And then you're looking for this little difference on the which is reflected from the mine. When the mine gets a bit deeper, say 5 centimetres, so again the reflection from the mine is in red, the ground is in, the no mine situation is blue, you can start to see a distinct reflection at a distance which corresponds to the time, which is the return journey from the pulse to go out through the ground, bounce off the air interface and any other discontinuities in the mine, and then come back to the receiver. And then that's clearly a nice detectable signal in this region here. As you move to 10 centimetres, the signal moves further along the x-axis. It takes longer for the signal to go out and come back. The signal's getting smaller, but it's nice and clear now. If we move to 15 centimetres, then the signal now is getting smaller. The signal gets small very quickly because the ground is quite attenuating. The ground doesn't transmit radio waves very well, so the radio waves don't propagate through the ground very well, so they get attenuated quite quickly. But most demining contracts typically specify up to 15 millimetres, so that's the sort of range of detection. So you can see there's an immediate problem. What you'd like is you'd like this pulse as sharp and as fast and as narrow as possible, so you could see the mines as clearly as possible in this region here. The problem is if you try and make the pulse narrower and narrower, you need to go to higher and higher frequencies, and they won't propagate through the ground very well. So it's just like Liam said earlier, there's always a but. You know, you'd want to go to higher frequencies to get better penetration, but to get better identification, but the ground won't let you do that. There's various signal processing techniques which are used to sort of take away the effects of the ground, remove the direct coupling. And for example, if we were just to subtract those signals, then you would see them very clearly. So some of the key challenges in ground penetrating radar, and that's one of the reasons why these systems have been difficult to get into widespread production, and there's only really 2 commercial systems which have come from the military field, Mindhound and HDMITS. Mindhound is a UK system, and HDMITS is a US system, both developed with huge amounts of research over the past few decades. The reason they're difficult to make is first of all, you've got to make them work alongside the metal detector, so they've got to be compatible. You need this pulse to ring down, be very narrow, and if you've had any experience of electromagnetics and designing antennas, everything wants to ring and oscillate. It's a bit like trying to make a tuning fork that just doesn't oscillate. It just does one cycle. It's quite challenging. Minimizing this direct signal is also quite challenging. Minimizing what we call clutter inside the detector is also challenging. The soil is very variable. Accounting for that's also not easy. There's variable ground surface, because obviously the person using this device is going to be sweeping it backwards and forwards over the ground. The distance to the ground will vary. The ground surface won't be flat. And then you've got all sorts of clutter targets, stones, rocks, roots, and so on. So just radar on its own has challenges, but the radar will uniquely identify the plastic content, the non-metallic content. So it's telling you something different about the target in the ground. So in terms of what you see in front, what we have here is sort of just shown in outline here is several coils of a metal detector around the outside, and then a transmitter and receiver shown as these triangular sort of bow tie shaped shapes in the middle. And we put all that together, it looks like that, and you can see the system at the front here with the radar and the metal detector coils. So what you've seen there is the radar trace on its own, what's called an A scan. So that's amplitude versus distance. It's essentially the signal you get at one point in the ground. If you were to scan the detector, and this shows a sort of setup we've got in the lab, which shows a tank full of sand. It's very idealised for laboratory conditions. It's sort of what we first started working on. We've probably not used this so much in the last couple of years, but a nice easy medium to work with. And if we were to bury a target, say, and what I'm showing here is a target that's buried 7 centimetres deep, and then if we were to sort of sweep a detector backwards and forwards, if we were to just sweep the detector over the top of the mine, and then we were to show the same data as shown before, so each one of these points along here is a single A scan, and instead of showing amplitude, I'm showing the signal as a colour scale. So red is big, red is very positive, blue is very negative, and green is somewhere in the middle. If we just pass over the mine itself, then you see the ground bounce from the top of the sand, and that's more or less flat. Those lines going across the top. And then as we pass over the mine, we see this sort of characteristic hyperbolic shape that's indicative of the mine. Now, if you've seen sort of ground penetrating radar traces before, widely used for detecting buried pipes and so on, which are deeper, what you typically look at is these sort of B scans with these these characteristic hyperbolic shapes really indicate the presence of something. So you can clearly see, moving to a B scan, the feature's a lot more identifiable. You can get an idea of what sort of size, what sort of depth. If you do a full scan, not just to take a line across, but you do a full raster scan over this area here, so that you have a full surface, what you can do is then look at the data from the top down. And what I'm showing here is what we call a C scan. That's like looking at the ground from the top, and you can clearly see the feature of the buried target there, very identifiable. So once you start sweeping over the object, you start to get a lot more information about it. And when the deminer's using a detector, they typically do this for them. They do this themselves. They'll sweep backwards and forwards over the detector, beep, 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 and they'll synchronise the sound, the detection of the buried object with the position of the detector. So mentally, they're sort of constructing these sort of images, if you like. Well, not really doing the images, but they're using that information. So here's a C scan from a real situation. This was a test site in Benkovic. These are PMA-3s. They're a type of sort of Soviet-made landmine, and a PMA-2, which is a bit smaller but contains more explosive charge. And then there's a coin buried at different depths. And clearly, when you do a C scan over this, you see the landmines, the bounce off the top quite clearly, and the coin. The coin is too small to be seen by the radar. So I'll give you a bit of a demonstration of that. Should be okay. Thanks. This is where I crossed my fingers and Liam got away with it, so I'm hoping I will as well. So it's probably a bit easier if I just walk into the field of view of this radar and you'll see what's coming in. The radar signal that's bouncing off me. So what you're effectively seeing is the display's been scrolled across like I knew there was a reason I brought this. So it's a bit like a chart recorder, scrolling across continually in time. At the top, anything close to the detector. At the bottom, anything further away. So if I take the mine that Liam was showing earlier on, and I sort of move that then in, you'll see it moving from the bottom in towards the top. Oops. Back again. So if the deminer's sort of sweeping over the top of that mine, then you'll get a display that looks, something like that. That characteristic hyperbolic shape that you were seeing in the plots earlier. So I hope that's useful. So that sort of shows you what the type of data that you receive from a ground penetrating radar GPR system. So the next thing is how can we get that data and use that to enhance detection or characterization capabilities? Because if you just to say take the signal from one of these, either the radar or the metal detector, and plot it versus time, you get a complicated plot like that as you scan backwards and forwards over the area. And obviously, the question is, where's the mine? So just having the radar and the metal detector signals on their own doesn't allow you to construct the A and the B scans, which you need to provide those type of images or process the data further. You need something about the position. So if we take the position, if we had a sensor that could track where it was, then you'd be able to plot position at the same time as you could record the signal, and you'd be able to then map out these. And this just shows to illustrate that the same situations before, different frequencies. So these would correspond to the different lines that Liam was showing in the metal detector plots. You would have an array of images, all at different frequencies, which you could then process. Much more data to process, much more data to then be able to characterize the object, position it, find its depth, find out what type of object it's likely to be, both for what I'm showing here for the metal detector, but also for the radar as well. So how can you get position? Well, you need to measure the position of the detector head to about 1 centimetre, and you need to do that about 50 times a second to keep up with the rate at which the detectors are moving. That's actually quite a challenging problem. There's a number of there isn't really an ideal solution yet in the field, but there's a number of most likely contenders. And what I've done is I've sort of summarised on the slide here some of the technical specifications it needs, and some of the issues the common solutions have. For example, it needs to have about a sub-centimetre resolution ideally, because the devices themselves, they're a few centimetres in size. It needs to be fast enough to keep up with the speed at which the deminers operate, and they typically sweep backwards and forwards maybe once a second. So you'd have to have enough points over, say, a metre to do that. So that gets you around about 50 points per second as being the minimum speed. It needs to be low cost. It needs to be light. It's got to be low powered because it's got to run off batteries. And so most common issues have issues with cost. GPS, for example, using satellite tracking has particular issues with multipath effects near the ground. You can get GPS systems to track to a centimetre, but you need reasonably clear view of the sky. And when you're tracking something at the ground with the D-minus legs nearby and other clutter items, trees, vegetation, walls, and so on, that's quite a challenge. There's often a need for separate hardware. It's got to be something that can work in reasonable weather conditions. So we've been working on an optical system, and these are just starting to come over the last few years. These have started to come commercially available camera systems on very small modules that could be put onto the. And this shows the output of a camera system, not necessarily this one, rastered over a ground, and you can see the density of the search pattern. So if you've got position now, not just radar, you've also got radar, you've got position, you've got multi-frequency metal detection, then you can start to put all that together. And this shows a scan that we did from Benkovic near Zadar towards the back end of last year, one of their test lanes of their test site with multi-frequency metal detection and ground penetrating radar side by side over a section of the lane. We've got position now, so we can produce these maps. There's a signal from the tail of a mortar bomb, just the metallic tail. Quite a big chunky piece of metal. It's also ferritic. It's steel, so a huge signal. Swamps a detector. Hardly a signal from the radar. There's a screw. It's metal, picked up by the metal detector. Doesn't have any plastic round it. There's a PMA3. We see the metallic components associated with the detonator, and there's the case, and then some metal fragments up at the top, and so on. So you can sort of see the capability when you put all that together. Of course, the D-miner doesn't want to look at maps like this. So what we need to do is integrate all that together in a sense which is useful to the D-miner. The D-miner wants to concentrate on, they just want a yes/no answer. Do they have to start digging, and where? Metal detection remains the dominant detection technology, and the reason why is driven by this very simple equation. Most landmines have metal in them, a small amount, but it's there, and it's just about detectable. It's quite challenging. No metal mines do exist, but they're fortunately very rare. And for most ex-conflict sites, it's known whether there are no metal mines. They're very rare, so that equation generally holds, but it's not universally true. So the process is slow because of the large number of false alarms created by metallic clutter. It's not just detection that's the problem. It's not just getting rid of those false alarms, because you've obviously it's part of a process. Once you detect, and even if you know it's a mine, it's still got to be dug out and dealt with. So a newer generation is needed. Smarter metal detection to discriminate, characterise, more dual mode, and position aware systems. So hopefully I've sort of solved the case for adding position because of the quality of the data you can get. So position is a key enabler towards maximising the potential of any algorithms, because we can then start to do some of the things that the more skilled metal mine operators can do. Scan over the device and use the response of the detector, put the detector on its side, find out whether the device is long and pointy or circular, or get a rough idea what depth it is. Then we can sort of build algorithms to do that. And what we can do is, if we put all that together, and this is data from the field, so it's measured, it's not simulated, is we'd have position. We'd have the spectral information that Liam showed you. So each of those points on that grid would have a spectra. Each of those points on that grid would have an A scan. From those A scans, we can then pick out characteristics in the frequency time domain, which are characteristics of the types of radar signatures we would get from different types of object. Shape, size, the size of the internal air gap, and so on. And this shows a sort of situation with a layout there with several different types of mine and several clutter items. And so we've potentially got a lot more data to use to discriminate. Now, of course, the operator doesn't want to see this. The operator just really wants to see, just an indicator. But this data is nevertheless invaluable. You could relay that off. You could store it, so you could learn from it. You could upgrade the algorithms. You could use artificial intelligence techniques, machine learning, and so on to enhance that. So, just looking towards the future, then, what could we do with sort of generations with a new generation of detectors that can do that? We could automate the data transmission from the detectors to a central node. So these things could send their signals back and they could be logged. So at the moment, the detector beeps, that's it, the signal's gone. There's no record of it. There's no reason why it couldn't be logged, and we could keep the position and integrate all that data into this sort of cube, which we could then process, this cube of data. That could be dealt with locally. And then, of course, the more dangerous devices, the passes over real devices, that data could be sent centrally. The algorithms could be updated. The system could learn dependent on the particular field conditions, the particular soil types that are encountered locally, and that could be improved. So it'd allow a layer of management. You could also do a live mapping of of whether the ground's been covered effectively by the operators, track position in real time, could streamline operations. It could be data driven, use all the Industry 4.0 type jargon, digital twinning and so on. It gives a layer of quality assurance, and essentially it provides if it's a difficult decision about whether we dig or no dig, there's potential for a second opinion, for an expert second opinion. That sort of signal looks different, so we should do something with it. Ultimately, though, we've got position, we've got signals, we've got a view like this. You don't want to show the operator an image in real time because they've got to look at the ground. But there are augmented reality technologies coming along where that image could be maybe projected into the deminer's field of view through their visor. So as they're looking at the ground, they see this type of data superimposed on their field of view, so you could possibly give them the perception that they're looking through the ground at the object. And without position, that's not possible. So that's potentially where it could go in a not so distant future. So yeah, I think it's probably about time for me to start rounding up and some concluding remarks. Hopefully, I've sort of you learned a little bit about the difference between the problem with a metallic clutter and uncooperative ground, and that's one of the key problems with humanitarian demining. A new generation of detectors to get away from just the over-reliance on metal detection would certainly be useful. The enabling technologies, the lower cost of electronics and so on. The GPR is becoming more proven, and the ability to integrate position is becoming there. We can see spectroscopy can add intelligence to the metal detectors. GPR, ground penetrating radar, can further improve that. Position tracking allows you to move from A scans to B scans and C scans, and much more smarter and intelligent algorithms. And ultimately, the complete integration of these subsystems could yield sort of a three-dimensional picture of the subsurface. So yeah, as you can see, good positional information, sort of a key enabler in doing that. So that's really sort of finish it. Just a sort of a little bit of a trailer of the sort of other research we do in the group. Humanitarian demining at the top here is one of our major activities now. But as you've seen, we've worked on security systems and continue to do so with the industry, various of the leading manufacturers. We also work applying magnetic techniques, these multi-frequency techniques across steel production, various industry processes and so on. We have an active program at the moment with Salford Royal, looking at is there any possibility to use electromagnetic techniques for medical diagnosis and continual monitoring. So it's quite a varied. Our specialism is electromagnetics, but we're very passionate about applying that and working with end users and taking these systems through to industry. And we've got fielded systems commercially spun out from a few of these fields. So we very much like to carry that process on in humanitarian demining. And I think that's where I should shut up because my buzzer's gone and I've had my hour. So I thank you very much for your attention.